So here's the problem. We have to find the approximate factorial of a very, very large number, a number which normally would be out of bounds for your normal Windows calculator. Let's see an example. So I fire up the calculator app. Um, if you put in like small numbers like 8 and find the factorial, obviously it wouldn't be difficult for the computer to compute that. But for example, if you put in a very large number, for example 10,000, and try to find its factorial, it'll just show you errors because the computer's memory is not large enough to accommodate the large number, which is 10,000 factorial. So is there a way around this? So that is the point of this video. So finding the approximate factorial of a very, very large number. So isn't it simple? For example, if you want to find a factorial of say 10,000, you just have to multiply 10,000 with 9,999 and then 9,998 all the way up to 3, 2, and 1. So as you can see, you would end up with a very, very large number. If you try writing computer code for directly multiplying numbers, all the way from, sorry, this should be 10,000, 9,999, 9,998, 9,997, all the way up to 3, 2, and 1. But as you saw just right now, in the example of the calculator app, it doesn't have that kind of memory to accommodate such a large number. Multiplying all these numbers would end up to a very, very large number. So computers would normally not be able to fit in such a large number um, into its memory. So we have to find a way out of this. So enter logarithms. So we'll be using logarithms to reduce the complexity of our problem. I've given an example here. Um, so while finding out the factorial, you basically have to multiply um, a lot of numbers. So let's say we are multiplying three numbers: 123, 450, and 900. Um, so the product of 123, 450, and 900 is a very large number, which is 4981500. It's easy to find out on a calculator, but is there an easier way to do it instead of just directly multiplying these numbers? So we will be using logarithms to do this. So first what we would do is calculate the logarithm of the product 123 into 450 into 900. Notice that this does not require us to calculate the product itself. This is because of a property of logarithms which allows us to separate separate the products um, into uh, into the separate logarithms of the individual numbers. So if you have three numbers multiplied with each other, the logarithm of the whole large number would be the individual logarithm, the addition of the individual logarithm of the numbers which make up the product. So this would be log 123 plus log 450 plus log 900. So what happens is, instead of multiplying these numbers, um, we are finding out the logarithms of the individual numbers and adding them up. So this converts a multiplication problem into an addition problem. And log of a number is much, much smaller than that original number. So let's fire up the calculator app and check. So for example, log 123. 123 is a three-digit number. So let's find out what log 123 is. It's 2.0899, which is just a two-digit number, a single-digit number with a lot of um, points after the decimal. Log 900, for example, log 900, for example, is another single-digit number with many points after the decimal places. So as you can see, you reduce 900 to 2.9542, 123 to 2.0899. So, and you just have to add these small numbers to get the logarithm of the huge number, of the huge product. And you don't have to calculate the product itself to find the logarithm. You just have to find the logarithm of the individual numbers making up the product. So what we do now is add the logarithms of the individual numbers, which in this case equals 7.6973. So finding the logarithm of the product did not require us to calculate the product itself. We only needed to calculate the logarithms of the individual numbers. So we just found out the logarithms of 123, 450, and 900 separately and added them up. So it's very simple. Like it's just adding up three small numbers instead of multiplying three huge numbers. Isn't that simple? What we get is 7.6973. So now we can just find out the actual product by using antilog tables. So the product just will be 10 to the power of 7.6973. That's your answer. But let's see. We can simplify this that 10 to the power of 7.6973 equals 10 to the power of 0.6973 into 10 to the power of 7. Now, is that making sense? Because this is scientific notation. Um, it's easy to calculate 10 to the power of 0.6973 since it's a very small number. 10 to the power of 1 is 10. So 10 to the power of 0.6973 would be a number between 1 and 10. 10 to the power of 0 is 1. So let's see. So fire up the calculator. So and 10 0.6973 10 to the, so it's like 4.9808. Okay, so the answer would be 4.98081 into 10 to the power of 7, which is around 49808,100. So this is our answer. Notice that this number that we obtained from finding out the logarithms and then um, doing the antilog of the same is actually not the same as the original number which we found out by multiplication. So the actual number is 49815,000, and the number which we found out using the techniques that I described is 4980818,100. Have a look, another look. So this is 498. These three numbers are the same, 498. After that we have 15,000 here, and here we have 08100. So there's some difference. So why is this difference coming? So why is this so? This is because when we find out the logarithms of numbers, we truncate a substantial portion of the logarithm. For example, log 123 is actually a huge number, 2.089999. It's actually an infinite series. But we have to truncate it at some point. So I truncated it at 2.0899 so as to make it more manageable. That results in a degree of error, nonetheless, which crept into the final answer. Anyway, so that's why I'm calling it approximate, and the whole thing is approximate. That's why I'm calling it approximate, not absolute. So we now try to find the factorial of 10,000 using the techniques used in multiplying these three numbers, 123, 450, and 900. We would just extend this into finding the factorial of 10,000. So we would just be finding out the logarithms of um, 10,000, 9,998, and so on up to the logarithms of 3, 2, and 1. And we would be adding this. If we just go through the route of directly multiplying these huge numbers, we would just wind up overstressing the computer. I'll just show it to you once more. If you try to find out the factorial of 10,000, it will just show errors, overflow. So it can't accommodate the large number in its memory. Um, so what we do is we find out the logarithm. So log of 10,000 factorial is basically equal to log of um, the multiplication of these numbers. So now we know the property in which the log of the product is equal to log of the um, individual numbers making up the product, the addition of the log of the individual product. So log of 10,000, for example, is a very small number, is 4. Compared to 10,000, it's just 4. I mean, it's such a small number. And so log 9,999 would be even smaller than 4. So you're just adding up small numbers. Maybe you're adding up a lot of numbers, but these numbers are small compared to multiplying the huge numbers, adding up logarithms of these numbers, which is actually very small. Isn't that a computational advantage? So we, instead of multiplying large numbers, we're just adding small numbers. So I've written a program to just um, add the logarithms of these numbers. So I fired up MATLAB. So this is a code which would calculate the addition of the logarithms of 10,000 factorial, which basically would start from a value of 10,000. So here B is 10,000 in the first iteration, C is 0. C basically stores the summation of the logarithms of the numbers. So we start with C is equal to 0 and then keep on adding um, numbers, the logarithm of the different numbers which make up the factorial. We first start with logarithm of 10,000 and then we decrease b by 1. So b is now 9,999 and then we calculate the logarithm of 9,999 and then add it up to c. And then we decrease b by 1 and then um, calculate the logarithm of 9,998 added up to c, which stores the summation of the logarithms. And then finally exit the loop when b is 1. I mean b not equals to 1, which means when it sees that b is equal to 1, it just exits the loop. So it just calculates the logarithms of 10,000, the 10,000 factorial. So let's run this, and the answer we get is c is equal to 3.5659 into 10 to the power of 4. So what we get here is a pretty small number compared to the uh, entire multiplication, the 10,000 factorial. This is much smaller than 10,000 factorial, but it's the logarithm of 10,000 factorial, which we easily found out by just adding the logarithms of the individual numbers. And that was simple, wasn't it? that did not require much computer memory, did not require much resources on the computer. So we just now take the anti-logarithm of this number. So the result we get is 3.5659 blah 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 into 10 to the power of 4. So see 3.56594, 3.56594 into 10 to the power of 4. So this is the anti-logarithm. Sorry, this is the logarithm of 10,000 factorial. So if you want to find out the actual factorial of 10,000, that would be 10 to the power of 35659 point this, which is basically equal to 10 to the power of, if we separate the numbers after the decimal point. Um, so we're basically writing in scientific notation. Um, 10 to the power of point 45427452077 and 10 to the power of 35659. So this number is equal to um, a very large number, very large number. Um, so 10,000 factorial would be approximately equal to, sorry, I'm really sorry. This is 35659. So 10,000 factorial would be approximately equal to 2.846259 into 10 to the power of 35659. Okay, so let's check up the web for 10,000 factorial. Let's see if it's there. So factorial of 10,000. So um, this site has a total factorial of 10,000. It's 35,658 digits long, which is approximately the same as what we found out here, 35,659. Okay, and the first few digits are 2.846259. Remember this, 2.846259. So see, 2.846259. At least the first 1, 2, 3, 4, 5, 6, 7 digits are correct in our calculation, and the exponent is correct as well. So it says 35,658 digits long. We have 35,659. That's because an extra, obviously, an extra digit is added. I don't know why.